Hey everyone, welcome back to the channel. Today we are starting a new visual guide, a series on one of the most important topics in Java, and that is memory. We will here talk about Java memory. Okay, so every Java developer uses memory. Okay, every single time, they write a code, but many beginners never get a clear picture of what actually happens behind the scenes. So the first question arises is where does a variable go? Okay, where is an object stored, and what is the real difference between the stack and the heap. So here in the first part, we will focus on exactly that, stack versus the heap. Okay, so we will keep it beginner friendly and make it visual and practical. We will be not moving on more heavy theory and no more confusing definitions. Just I will try to put a simple pictures, clear examples, and easy analogies with the real life, so that will help the concept to stick. By the end of this video, you will be able to look at Java line of code and understand where each piece of data lives in memory. Okay, so this part would be one of a 4-part series on what happens to our data in memory. Okay, so let's begin with the foundation, how Java really works. Okay, so basically before we jump into stack and heap, let's quickly answer few questions. Okay, but question is, why should we even care? So there are various reasons, but 3 big reasons are: first is bugs. Okay, some of the most common and scary Java errors like null pointer exception, memory leaks, and out of memory error become much easier to understand once you can actually picture where your data lives in memory. Okay, so these errors everyone of us have heard of at least once in a life. Okay, so we will picture this all error once we know where our data lives in memory. Second is performance. The stack is fast and simple. Okay, data comes and goes automatically as methods are called and finished. Okay, the heap, on the other hand, is where objects live, and it involves like memory allocation, references, and later garbage collection. So when we understand the difference, we will naturally start writing cleaner and more efficient code. Okay, and the third is not the last, but one of the most important is interviews. Questions like what is the difference between stack and heap, or how does garbage collection works, are very common in Java. Okay, so if we can visualize the answer, explaining it would be much easier. So these are not just the theory topics, they help you debug better, write faster code, and explain Java memory with confidence. Okay, so let's build a clear picture step by step. So now let's look at the bigger picture. Okay, where does your Java program actually live when it runs? Okay, so when we start a Java application, the JVM asks the operating system for a block of memory. Okay, you can think of it as the JVM is getting its own slice of RAM. So whenever JVM asks the operating system for a part of a memory, it basically takes the slice of a RAM from the memory. Okay, then JVM divides that memory into different regions. Okay, few of them are like stack memory, heap area, metaspace, and few others. But for day-to-day Java programming, 2 regions are most used in the most of the work, and those regions are stack and the heap. If you see the stack part, each thread gets its own stack. The stack keeps track of method calls and stores local variables. Okay, local variables plus method calls all are stored in stack only. So, and if you see heap, right, this heap is shared by all the threads in program, and this is where every object we create with the new keyword lives here. So whenever we will create any object with the keyword new, that object is going to be stored in heap only. There are also some other areas like metaspace, okay, which stores class related information, but we will talk about that in next part of the series. For today, let's focus on the simple thing, the stack versus the heap. Okay, these are the two memory regions we basically interact daily with almost every time we write our Java code. Okay, so now let's use simple mental model that will make stack and heap much easier to remember. Okay, think of the stack as a notepad. Okay, consider the stack as the notepad, and it is basically placed on our desk. So when you are working on any task, what we do? We quickly write things down on the notepad. That notes are neat, small, and temporary. Okay. As soon as a task is finished, what we do? We tear that page from the notepad and throw it. Okay. So what we do? We know that that notepad is temporary. So once a task is done, we tear the page and throw it away. So this is how stack really works. It is fast, organized, and short-lived, as this analogy is here for the notepad. Okay. So now think of a heap as a giant warehouse. Okay. So the warehouse stores the actual big items. In Java, those big items are like objects. Okay. Whenever we create objects, those are the big items. But we don't carry the whole object around us. Okay. Instead, what we do on our notepad, we only write down the where the object is stored. Okay. And that location is considered a self number in our warehouse. Okay. And in Java, we call that self number as a reference. Okay. So the stack may hold a variable. Okay. Stack holds the variable, but if that variable refers to an object, okay, that actual object lives in the heap memory. So keep this picture in your mind. The stack is a notepad. Okay. The heap is a warehouse, and a reference is the self number that connects stack to heap. Okay. So now let's zoom in on the first memory region, the stack. Okay. The main job of the stack is to track method calls. Every time a method is called, Java creates a new stack frame. Okay. You can think of a stack frame as a small workspace. Okay. For that particular method till the time that method is running. Okay. So yeah, stack frame is like a small workspace for that method till the time that method is running. Okay. And that frame stores the method's local data. All local data related to this particular method is stored in this frame only. And local data is like primitive values and references. Okay. Whenever the method finishes, its frame is removed from the stack automatically. It simply disappears. Consider it like that as of now. So there are few important things we have to remember about the stack. First, it works in LIFO order, which means last in, first out. It is just like a stack of plates. The last plate you put on the top is first plate you take off, right? So whenever you stack the plates, the plate which you will put in the last, you will take that plate off first. So last in, the first out. Second, the stack is extremely fast. Creating a space on the stack is basically just moving a pointer up or down. Okay, consider these are the stack of plates we are putting here. So what we are doing, 0, 1, 2, we are just moving a pointer up whenever we are putting the data in the stack. And whenever we are removing from the stack, we are just decreasing the pointer from 2 to 1, 1 to 0. Okay, in this way. Third, every thread has its own stack. Okay. So if your program has multiple threads, each thread gets a private stack for its own method calls. Okay, so every thread runs on its own private stack. Fourth is the stack is auto managed. You do not manually clean it up. Okay, as soon as the method returns, its stack frame is removed. And fifth is the stack holds two main things: primitive values plus references. And these references are the self number in our warehouse, which we discussed. So primitive values are things like int, double, and boolean. References are self number from our earlier analogy. They point to objects that live in the heap. Okay. If you see this part in the right side, this, okay, you can see like three method calls stacked on top of each other, like main. First is main, then load data, then parse. Okay, and parse is running at the top. Whenever parse finishes, okay, its frame will be basically popped off. Okay, whenever this is finished, it will be removed from here, and execution will return to load data. Whenever load data finishes, its execution will finish and it will return its control to main. So in this way, frame gets popped off. So now let's see the stack in motion. So step one here is main starts running. Okay, as Java pushes a new frame from the previous slide, consider it like that, and that frame is a method is called greet. Okay, we call greet from main. So Java pushed another frame on top of main. Okay, here this is greet now. Still main is there only, it is not disappeared as of now. Still it is still there, but it is paused. Consider this color as it is paused now. It is waiting for greet to finish its task. Okay, so if you see in step 3, whenever greet finishes and it returns, this greet frame is removed from the stack. So the greet frame pops off and now we are back to the main frame. Okay, and now in step 4 what we see is main also returns, so this frame also gets popped off and now our stack becomes empty. Okay, so this is how stack works. This is the basic rhythm of the stack. Like when a method is called, a frame is pushed on top. When the method returns, that frame is popped off, removed. It is removed whenever it returns. Since newest frame greet was the newest one here, it returns first. We call this last in first out. The one which is most recent gets removed first. That automatic push and pop behavior is exactly why we never manually manage the stack memory in Java. It is auto managed. Now let's see the second memory region we discussed, the heap. Okay, the rule is simple. Anything which we create using the new keyword, okay, that will live here, that gets stored in the heap, and that includes like all objects and arrays and the fields which are stored in that particular objects and arrays. For user object, consider here name and age we have are the fields of that object that also get stored along with the object. So like you can imagine the heap like our warehouse from earlier slides. Objects are placed across all the available space we have, just like we can say from the warehouse different boxes shown on the slide. Okay, consider it like this, different boxes, they are freely placed wherever they get the space. Okay, unlike the stack, there is only one heap for the application. Okay, for all application there is only one heap map, and that heap is shared by all threads. This is shared object storage. Okay, all threads share this memory. So the heap is also much larger than the stack. So since it is larger, it can store bigger and longer lived data. But using this heap memory is slower because objects needs to be allocated, tracked, and eventually cleaned up. whenever they are not getting used. And this is one of Java's big conveniences for us. We do not have to manually free heap memory. In languages like C or C++, if someone has idea of it, you often have to explicitly release memory using things like free or delete. Okay, but in Java, the garbage collector handles this all things for us. It automatically finds uh, objects which are not longer being used, and that it reclaims those memory for us. Okay, and we will cover garbage collection properly in future parts. But for now, just remember this: with new keyword, objects are created, and Java cleans up unused heap objects automatically. So the most important idea in this whole series is this current slide, the reference. Okay, so now look at the line. User equal new user. Two separate things happen here. Okay, first, new user creates an actual user object. Okay, and since it's an object that lives in the heap area. Second, the variable user we have here, okay, is created inside the current method stack. Okay, consider this is the method stack we have, and it is user variable is created here. Okay, since it's a variable, it will live on the stack only. But key point here is the variable user doesn't contain the whole object. It only contains the reference. Okay, it only contains the reference to the object. Think of the reference as an address or like a self number from our warehouse analogy. This is what the arrow represents here. This arrow. This stores the address where actual object is stored. So reference means address. So the variable is not the object. The variable points to the object. Okay. So the whole idea of this slide is the variable is not the object, it points to the object. Okay. Keep it in mind. Okay. Now we have seen various ideas. So let's trace some real Java code line by line. Okay. So if you see here, we have a simple demo class. Okay. With one method called start. Inside start, three things are happening. First, we declare an int variable and we are calling it a count and setting it to 5. Second, we create a new dog object with the name Rex we are passing and storing it in a variable called d. Third, we call d.bark. Okay. So over the next few slides, we will see how memory changes as each line runs. Okay. There are 4 things we should watch for in the next few slides. First, a new stack frame will be created for the start method. Okay. Second, the primitive value count equal 5 will be stored directly in the stack frame. Third, a new object dog will be created on the heap memory. And fourth, the variable d, okay, will store a reference that points from the stack to the heap object. So now keep this code in mind and let's see step by step. So step 1, if you see, we have start, right? When method starts running, it will, as soon as the method starts running, it will Java will push it to a stack frame. Okay, so for this method a new stack is assigned. Now when we reach the line int count equal 5, this line, okay, count is an int, okay, and int is a primitive type. Okay, int is primitive. Since it is primitive, it is small, simple data. It is not an object. So Java stores the actual value directly inside the stack area. Okay, Java will directly store this value in stack area only. In this case, the value 5 will live right there on the stack only. So no object is created as of now. So the heap is not used at all. Okay. So whenever the start frame starts, count 5 equal count equal 5 is stored in the stack area. Heap is still empty because we have only processed line 1 only int count equal 5. So at this point, everything is living on the stack only. So if we see in the step 2, we will reach line 3, dog d equal new dog with the value x. Since we are using the keyword new and creating an object, this tells Java to create a real dog object, okay? And that dog object would be assigned a memory, where since it's object, it will be assigned a memory in the heap area, okay? Now if you see the stack, okay, inside our start frame for the stack start method, okay, Java will create a variable because variable are stored in the stack only, okay, and we are calling it a d, but d is not actually storing the dog object itself, okay. D is actually storing the reference to the dog object. Reference means address to the dog object where dog is stored in the heap area, okay, and that reference is like an address, we can consider it. So it tells Java where the actual dog object lives on the heap, okay. So if you see, there is also one more detail here. Text we have, right? The text we passed Rex, okay, that will also live on the heap area only. Rex text also lives in the heap area only along with the dog, since because it's a dog object's name field, okay. So if I say in one line, Java created a dog object on the heap, created a stack variable called d, and stored a reference from d to the dog object, okay. And if you notice that count equal 5 is still stored here, okay, inside the stack frame. So this is the difference. Primitive stores their values directly, okay, in the stack, while object variables store references, okay. Primitive values are stored directly, while object variable, like d is the object variable we have, they store the references. So now if you see the step 3 here, in step 3 method will finish, okay. So when start returns, okay, whenever the work of start method is done, it will be popped off from the stack, okay. The stack is removed immediately. That means everything inside that frame disappears too, okay. So count is gone now, okay. Count was inside the stack only, and since the reference variable d was also stored in the reference in stack only, that is also gone. This is why stack cleanup is so fast and automatic. When the method ends, the whole family, whole frame simply pops off. But let's see the heap now. The dog object is still there, okay, but no one is referencing it, okay. Important difference is this only, no one is pointing it to anymore. The reference d used to point to it, okay, but d disappeared whenever the stack frame was removed, okay. So now dog object is unreachable, and an unreachable object is considered garbage, okay. So what is garbage? Okay, in heap memory, an unreachable object is no one is pointing to it, there is no reference for it, okay, is a garbage. But Java will not unnecessarily delete this dog object, even though it is garbage as of now, but Java not necessarily deletes that object immediately. It only becomes eligible for garbage collection, okay, since no one is referencing it, so it is eligible now for garbage collection. Later the garbage collector will run, find objects that can no longer be reached, and reclaim that memory, okay. So the stack cleans up instantly when a method returns, okay. Heap is cleaned up later by garbage collector, okay. We will see this in detail in other parts of our videos, okay. So now let's turn everything we have seen as of now into a simple rule, okay. In Java we have basically two kinds of data to think of: primitive and references, okay. Primitives are like int, double, boolean, char, long, etc. A primitive stores its actual value directly in place, okay. It means directly in stack frame. So if a primitive is local variable inside a method, it lives directly inside that method stack frame, okay, directly on the stack. So this is what happened with our count equal 5. But references are different. Whenever we work with the objects like dog, string, arrays, or user, right, that actual object lives on the heap. The variable doesn't contain the object itself. Okay, the variable only contains a reference or addresses that points to the object on the heap. So the object lives on the heap and the variable points to it, and that variable is stored in the stack memory. Okay, there is also a common myth among the people that primitives always live on the stack only. This is not completely true. A local primitive variable lives on the stack. Okay, but if a primitive is a field inside an object, okay, if primitive is a field inside an object, like consider we have a dog class, okay, and its int is a primitive value, int is, okay, it won't be stored in the stack. It will be stored along with the dog object in heap memory only. Okay, so the better rule is this: local primitive variables live on the stack, objects live on the heap, okay, and primitive fields live wherever their object lives. Okay, this detail is useful, remember it. So now let's compare the stack and the heap side by side. First, what do they store? The stack stores method calls, local variables, references. Okay, heap stores objects, arrays. Okay, everything basically we create using the new keyword. Next is sharing. Are they shared? No. Stack is private, one per thread. Each thread gets its own stack. But heap is shared by every thread. Okay, all threads in the application use the same heap. Per application, we have one heap area. Now let's talk about speed. Okay, the stack is very fast. Okay, because just we have to move a pointer up or down. Heap is slower because the JVM has to find a space. Okay, allocate the object and later track it if it is not being referenced for cleanup. Okay, for size, the stack is smaller. Okay, if we talk about size, stack is smaller, but heap is large. Okay, because it is shared, so it should be large so that everyone can use it. And if we talk about the lifetime, okay, stack data lives only until the method returns. Okay, and heap objects live as long as something can still reach them through their reference variable. Okay, once no one references it, okay, and no references remain, they become eligible for garbage collection. For management, if we talk about, the JVM handles the stack memory. Okay, it is handled automatically through method calls and returns. Okay, the heap is cleaned up by the garbage collector. And finally, when they run out of space, what error we get? We get stack overflow error whenever stack memory is full. If heap runs out of space, we get out of memory error. Okay, so that is the quick comparison. Stack is small, fast, private, and tied to method calls. Heap is larger, shared, object focused, and cleaned up by garbage collection. Now let's look at these two errors, stack overflow error and out of memory error, clearly. So now let's connect the two errors. If we see, we have a stack overflow error, okay, and we have what, out of memory error. This happens when the stack runs out of space. Okay, every method call adds a new frame to the stack. Okay, so if a method keeps calling itself again and again, like it is calling in a loop again and again without ever returning, the stack frames keep piling up. Okay, when they keep piling up, they are using some space from the stack space. So what will happen? Infinite recursion will happen. Okay, so this method never stops calling itself. So the stack keeps growing until there is no room. Okay, no memory is left. That gives us stack overflow error. On the right, we have out of memory error. Okay, this usually will happen when the heap runs out of space. For example, if we keep creating an object, okay, with the while loop, it will run till unless we are out of memory from the heap. Okay, when we create too many objects, okay, at some time, at some will reach a time where this whole memory would be used. Okay, so we'll get this. So when those objects stay reachable, what happens? Garbage collector cannot claim them. Okay, Why? Because we are storing it in the memory, so heap gets stored. Garbage will not use it because it's still getting referenced. Okay, so garbage collector will not claim them. Eventually, what will happen? Heap will fill up. Okay, so practical takeaway from here is, if you see a stack overflow error, investigate the stack, usually recursive method calls. If you see an out of memory error, we have to investigate the heap, usually object allocation or references that are keeping objects alive. Okay, once we match the error to memory region, we will already know half of our work is done where we have to look at. Okay, so this confuses almost everyone, and it falls straight out of where we just learned. People argue almost many times like Java is passed by value or passed by reference. Okay, simple answer is Java is always passed by value. Okay, but when you pass an object, the value being copied is the reference. Whenever you pass an object, value being copied here is reference only, and reference means that. So the method gets a second remote control, we can say, pointing at the same object. So we see we have two different examples here. If you change the object fields through that reference copy, actual object would be changed. Okay, and the caller absolutely will see it because both points to the same heap object. On the right, if you reassign the parameter itself, okay, like if you see in the right, reassign the parameter itself. So x equal new dog, okay, max we are passing. It was a reference variable which got copied, but now at this variable we provided a new object. Okay, so basically caller will see nothing. Why? Because we only repointed to our local copy. X is here local and they don't have access to this X. Okay, so caller's dog will be unchanged because it's only a local copy which was repointed. Okay, okay, so let's log what we have seen as of now. We'll recap it in 5 lines. 1. The stack is for method calls. Okay, each call gets a frame with its local references. Okay, it's LIFO, last in first out. It is fast and auto cleaned whenever method returns. Second, heap store objects. Everything which we create with a new keyword will live here. It is a one shared space for one application. Since it is a shared space, it is generally bigger, and it is cleaned by the garbage collector whenever a reference is, when no one is referencing for that particular object. Third, a reference is just an address. Okay, the variable which points to the objects on the heap. Okay, it's a reference. It is not an actual object itself. Okay, primitive values are stored in place in stack area. Okay, local ones on the stack. But any primitive fields with the object, they will get stored in the heap along with the object. Java passes a copy of the reference. Okay, so Java is a pass by value. Same object, we provide a different remote control. Okay, this will clear your why Java is a pass by value. Okay, so as of now we have understood the foundation of Java memory. Now rest of the series we will build on top of it. Okay, in part 2 we will go more inside the heap, because the heap is not one big empty space. It is divided into areas like young generation, old generation. We will look at Eden space, survivor spaces, how objects age over time, where Java keeps things like the Spring Pool. Okay, in part 3, we will focus on garbage collection. We will see how Java decides which objects are reachable, what GC routes are, how mark and sweep works, the differences between minor, major, and full garbage collections. We will also talk about modern collectors like G1 and GGC. And in part 4, we will try to do more practical. We'll look at memory leaks, okay, and how to read an out of memory error, what heap dumps are, which JVM tuning flags are actually we should see. So if stack and heap made sense today, we'll see for the more deeper parts. If this video helped you, please leave a like and subscribe to the channel.